Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're back on the Soroc IQ 120 data terminal, which in the last part, which if you haven't watched yet, I recommend you watch that first. We're continuing on where we left off, as per usual, link down below. I took this thing apart. This is the power supply / CRT driver board for this thing. I wanted to check about this capacitor, maybe reforming it. And when I flipped this over, we saw absolute carnage and destruction on the bottom of the board. Some kind of flashover happened and burned up a bunch of the PCB. So in today's video, I guess I have to decide where I'm going to go next with this thing. There are a few possibilities here. Try to rebuild this power supply or replace the power supply. And on top of that, the monitor obviously has got issues with the CRT and it's leaked all over the place, which also might have damaged stuff. But I think the very first thing we need to do, obviously, is deal with the power supply problem, because I need to try to power up the computer, see if it's even working, and there's just a lot of stuff to do. So without further ado, let's get right to it. Okay, let's talk about options. If I'm going to be rebuilding this power supply and relying on the linear regulation that's happening on here, obviously we have to sort out this broken part of the PCB here. I'm assuming I could try to clean it, maybe to expose exactly what's happened here, and maybe with a bunch of scrubbing, getting this black carbon off, the PCB itself is okay. Now, one of the issues with this PCB, and you probably noticed this in the first part, is there is no solder mask or solder resist over the board, right? These things, the traces and everything, all totally exposed. Unfortunately, that can help exacerbate these flashover type events, because believe it or not, that solder mask or any of the coatings that go on top of it actually help prevent arcing between the traces, at least to some degree. So if there's any hope in trying to rebuild this thing in place, then obviously cleaning is going to need to happen and some reconstruction of this area of the board. Now, it's entirely possible that this tall 30,000 microfarad cap is actually good still. Maybe it wasn't actually damaged, and cleaning up the bottom of the board and getting this thing off will allow us to test it and try to reform it and stuff like that. And in fact, it's possible this whole thing actually is working right now. I mean, once I clean this up, there might not be even a fault. Maybe no traces even got eaten. Who knows? This question still remains. What exactly happened to cause that flashover event? There are a few things I can just check quickly to see if there's any faults on this board. These 4 diodes right here, maybe one of those is shorted. So I'm going to need to go through and check that those are shorted. We can also check the voltage regulators on there. There are 3 of them, 2 15-volt ones for the CRT and the 5-volt one for the main board. So we can check for shorts on those. Another thing that's worth checking is the transformer that's in the main chassis. I'm worried that something might have happened to the transformer, like maybe a short internally that allowed 120 volt mains to pass through to the secondary side of the transformer, which is what feeds into, well, these various components here. Now, I took a look at the schematics that were in the manual that I found online, and it seems that the transformer has 3 sets of windings on it. One of them goes to the 5-volt rail, another one goes to the 15-volt rails, the 2 of them that power the CRT, and the third one goes to the motherboard that goes to that 7912 voltage regulator that creates the minus 12-volt rail. That's after going through a bridge rectifier and those caps, of course. And that minus 12 volts is then used to create a minus 5-volt rail, and that is done with the help of a Zener diode that's on the motherboard. And in addition, that third winding that goes to the motherboard is also used to create a plus 12-volt rail, and it's also using just a Zener diode. What the 3 windings in that transformer mean is that one of those could have failed, like the one that goes to the 5-volt rail here, that carries the most current. And if that sent 120 volts or some higher voltage into this rectification circuit, that might have exacerbated or caused that flashover that we see. And it also might have damaged parts of this board, or potentially, if the 5-volt regulator shorted, it could have gone through to the motherboard and caused some massive damage there. Let's not think about potential damage to the motherboard right now. Let's just think about the power supply. Now, in my parts, I found this. It's a little switch mode power supply. It's pretty modern. I think it's from 1999. I don't remember where I got this. I probably took it out of something that I recycled. This supports 5 volts at 5 amps and also has a plus 12 volt rail and a minus 12 volt rail. And the good thing about that is this one little power supply should be sufficient for powering up the entire motherboard. We could generate the 5 volts the motherboard needs directly with this, bypassing all that stuff on that board. And then the minus 12 volts could feed into the motherboard after the 7912. So I could just take that regulator out. The minus 5 volt rail will still be created with the Zener diode that's on there. And then we could just feed the plus 12 volt rail from this after the other Zener diode that creates that 12 volt rail. So with this little power supply, that goes a long way to replacing the entire transformer and all this bulky regulation stuff, and would power the motherboard directly. That does leave us with a little bit of a problem though, if I were going down that route. The plus 15 volts that runs the CRT is coming off that third winding, or one of the windings on the transformer. And when you have an AC transformer and 3 different windings, the windings affect each other. So imagine you have 3 windings on the transformer and they're all identically creating 5 volts each. Well, if you load down one of them, that affects the voltages on the other 2. And when you run an AC transformer with no load altogether, if you measure the AC voltage coming out of the transformer with no load, it's going to be much higher than it would be once it's under load. Well, the 5 volt rail that's regulated by this big chonky heatsink regulator here, that obviously draws the most load through the power supply. And it's pretty consistent because you turn on the computer, that whole motherboard powers up with all those TTL chips, and that should bring down the voltage on all of the rails as that load is applied, including the 15 volt one for the CRT and the 12 volt one that's going into the 7912 on the motherboard. Well, if we take away the load from the motherboard and the 12 volts that are on the motherboard, then it's quite possible if we go to power up the machine without any load on the 2 windings that are replaced with this little power supply, what's going into the CRT board for the 15 volts is now going to be too high voltage. It's probably not going to be too high voltage for it to work. These things are typically good up to the 30 volts, these regulators here. But the issue is the higher the voltage, the more heat it's going to be generated because the more voltage it needs to drop. And these little heat sinks that are on this board here are pretty small. So I think in a long-winded way what I'm saying is that if I have to replace the power supply with something like this, I'm going to also need to replace the 15 volt power supply on this board with another switch mode power supply that's 15 volts. And I thought I had one. I looked through all the little PSU boards I have like this, and I could not find a 15 volt PSU. If that were the case, it'd be pretty easy to get this thing up and running. Just simply rip out these voltage regulators, power these up directly from the mains, and then feed the voltages directly into the board here where these regulators sit, and it generally should work fine that way, just leaving all the other capacitors and stuff in place. Obviously this large cap here, that's all damaged on the bottom. This part of the board won't be used anymore, so we don't have to worry about that. We could just remove those components, but theoretically we should be able to get this thing up and working. So I think what I'm saying here is that we have 2 choices. I either revive this power supply here and try to fix this damage, potentially replacing the cap with this one here. It's 18,000 microfarads at 30 volts, just happens to be one that I found. Obviously it's not the right size, so I have to get creative with the mounting and stuff like that. Or I need to go all out and replace everything with switch mode, and that means I'm gonna have to order something to power up the monitor because I don't have the small switch mode power supply to do that. If we go that route though, what I can do is in the meantime, I can use my bench supplies to supply 15 volts for testing purposes while we use this, and then we can see if we can get everything up and working. If we think about this terminal though, from a purity standpoint or keeping it original, I think the best thing to do would be to try to revive the existing power supply here. And in that case, what we need to do first is take a look at the transformer that's on the chassis and power that thing up, not plugged into anything, and measure the 3 different windings coming out of that thing, just to make sure that everything looks like it's within acceptable values. So with that said, I'm gonna clear this stuff all off the bench. I'm gonna get the bottom of the chassis over here onto the bench so we can do exactly that. All right, so before testing the transformer, just because it's heavy to move and I have this on the bench already, let's test this thing. Let's check for shorted diodes here, and we'll check that the regulators are not broken as well. So multimeter is set to diode test mode, and the chunker of the diodes we should be able to test from the top side. So we're looking for diode drops and not shorts. All right, that seems fine. That seems fine. I guess it's a little high. I guess that's a little bit lower than I would have expected. I mean, generally we're looking for anything that's shorted, and all of these seem to be operating fine. We're seeing kind of an expected diode drop. So that's good. No damage here to the diodes. Let's check this stuff here. I'm still on the diode test mode here. All right, so we're getting a normal diode drop there across these 2 pins. Voltage regulator is a 3-pin device. but we shouldn't have a short between these pins. All right, there's a short there. I'm pretty sure we should not be getting a short between this trace here, which makes its way up into the burn area, this one, and these ones. Why exactly is this shorted here between there and there? That is very worrisome. Now what I might need to do is actually remove this component from the board. It's just hard to know exactly how this is connected. I guess I should check the schematic, but there are a couple nuts on the top and then we can desolder the 2 pins to pull that off. I think that's what I'm gonna do next. What concerns me is that this thing, if it's shorted between the output and the input, that means that whatever DC was going into this thing made its way to the motherboard directly. That would be basically catastrophic, and that would pretty much end this video entirely. We'll know once I get this thing out of the board though, if that is indeed the case. All right, first step, get these nuts off of here, and there's several washers. And now we just get these pins off. Oops, wow, that whole thing just fell off. So when you look at these packages here, there's actually an insulating plate or pad between it and the heatsink. And if you're gonna be testing, you gotta clip onto the top part, onto the metal. So now if I touch there, so that's on the body itself, there is continuity. And let's test against these 2 pins. It's fine. Oh, and it's fine. And we go to diode mode, 0.7, 0.6. But that's good. That means that this part itself isn't shorted. Why were we seeing a short on here? And my assumption is it should still be there, even with the component removed. And this was the trace coming from the burn area. And it is. We're still getting that short. Here's the page from the schematic showing the power supply, the 5-volt power supply that is. So those are the diodes we checked. Those are all fine. There's that large cap. It's 15,000 microfarads on here, but it's 30,000 on this board. Here's our voltage regulator, and this particular part isn't just a straight 5-volt regulator. It actually is adjustable, and that's why this extra pin comes down here, and it goes to a potentiometer, which has a voltage divider between the 5-volt rail, or the output of the regulator, and the ground, which is labeled return in this case. And when we look at the board, this large flood fill, this is the ground, and it goes to the connector that goes to the motherboard, and that's coming from over here, and that matches the schematics. Well, what we were seeing was a short between this and this. Now I think that might not be so much of a problem necessarily, because this is actually the output pin that makes its way over here to the connector that goes to the motherboard. The 2 lugs here goes over here to these components. This is obviously the voltage regulator, so there's a potentiometer on the other side of the board that goes into. And we're seeing a short between here and here. But I guess the issue is it's unlikely that these disc capacitors here are shorted. That is not likely. What's more likely is this goes down to this potentiometer, and I don't really know how this is adjusted. We should probably switch the multimeter from continuity mode into resistance mode. We should see if there's any amount of resistance. Say there's like 10 ohms or something like that. Well, then that's going to make its way here, and it will go over to this. The ground and VCC rails here coming out of the rectifier, they might be shorted due to that blast damage. And in that case, you might see like 10 ohms through this potentiometer and then through the short here and back to this side right here. All right, so this is the positive voltage that's coming from the rectifier. It's this pin here. Remember, we're seeing a short right to there. Oh, and we're also seeing a short to ground. Okay, so it's shorted across there. I should have tested that earlier, to be honest. All right, so we know for sure that something is horribly wrong and there's a short over here. I mean, for all we know, maybe this cap is just shorted. It looks like it's still actually connected to the board. I think what I'm gonna do is I'm gonna grab a brush and I'm gonna try to scrub this to try to clean up some of this carbon so we can at least see what exactly is going on here. One thing I can smell while trying to desolder this cap is the horrible burned electronics smell. Really, really bad. Okay, the cap, it's been removed. That's some serious leakage, yeah. And looking at the PCB here with the cap removed, let's just get this glue off of here. It's, I think, silicone or something, because it's definitely not hot glue. It doesn't come off as easily as it should. Anyhow, is that blast damage under there too? I'm assuming it is. So the flashover seemingly started on this side of the board here. And I think this little spot right here, if we flip the board over, that's this little space right here where it's just completely obliterated. All right, well, what I'm curious about is with the cap removed, do we still have a short? Mega ohm, mega ohm, mega ohm. That's nothing. So yep, the short is gone. We're at 2.8 mega ohm now. So I think our issue might have been with the cap. Let's see here. Yep. Yep. Yeah, yes indeed. Between that pin and these on the outside, all three of these outside pins are common. Originally, this cap, I guess, had multiple values: triangle, square, semicircle, and then nothing. But I think this is not a multi-value cap. This is a single value cap. Yeah, it just says 30,000 here. But it has failed and gone short internally. And I guess that really begs the question here. When did this fail? Did this fail a long time ago and that took this thing out of commission? Or had this failed just due to time and then someone tried to turn this on, which kind of blew out this whole section of the board here? So I think what I need to do is I'm going to use the Dremel here to try to clean this up a little bit, just so I could see what's going on. It's still hard to tell because it's so blackened, and we'll see how it looks. All right, well, there we go. This is salvageable, I think. I really tried to focus on the space between the traces here because I wanted to get rid of any carbon that was on the PCB itself. So when it comes to this replacement cap, I think what I'll just do is I'll just solder these wires on with these connectors through these holes here right onto the board. I'll put a bunch of the lead here so it gets a good connection. And then this will just have to be mounted inside the case with zip ties or something. And that should work. So I just want to take off this bleed resistor though, 680 ohms. I don't think that's necessary. Well, that's a bit of a problem. It seems like this is stuck. What happened here? I don't remember where I got this, but I think I just cut it out of whatever it was in. And obviously these screws, they're kind of fused on here. I'm going to try the impact driver on here. Well, it worked for one, sort of. I think these are maybe Loctited on. That's the only explanation for what's happening here. I have never experienced this. Okay. Yes. Red Loctite. Oh boy. That's one of the problems with red Loctite, is it's impossible to take off. Blue Loctite, on the other hand, that would have been easy to remove. Glad I had the old impact driver here. All right, there we go. It's not perfect, but it is absolutely, it's good enough. This should work now. Of course, once I put this back in, the regulator, and assuming the transformer is still good. But I'm pretty sure this cap failed catastrophically, causing the flashover, and that beefy transformer is hopefully fine. All right, let's just double check that this stuff is not shorted. All of this seems good. That should be like that. That's fine. Yeah, okay. We're looking good. And over here, same thing. We're looking good. No shorts. Okay. What's cool about these packages, you can't put them on the wrong way. The pins are offset to one side. All right, that's reattached. While I'm here, I'm just going to reflow these connectors. Since we all know broken solder joints cause all sorts of issues. And I may as well reflow these regulators over here, the two 15-volt ones for the CRT. And there's a couple connectors for the yoke. I don't see broken joints, so they seem okay. And we have this one here, which is what feeds the AC voltage into this thing. And then we have this bridge rectifier over here. And finally, there's another connector right there. Plus a little mini regulator. That looks fine. All right, well, at least from a bad cap perspective, I think this thing is okay. The one thing I can see that's sort of problematic here is I'm getting ahead of myself, right? The CRT neck connector here is a bunch of goop in there from the leaking glue. Does it clean off that easily? Oh yeah, the IPA seems to have an effect on it. Well, that's good. This is really gross stuff though. I've pretty much written off the CRT that's on there. And if the deflection yoke is bad, well, we're just gonna have to figure out what to do with that. But at least we want this connector to be okay. I do have spares of these, so it's not the end of the world. If it's too far gone because of this corrosion. But it does seem to clean off with the IPA, which is good. All right, I'm happy with this board. I think the next thing to do is, well, let's just see if this capacitor is working. I'm gonna hook it up to the bench power supply, and I'm gonna try to do the reforming. So what I'm gonna do, and I don't know why I haven't done this before, is try to use the virtual bench. This thing actually has a DC power supply on it. And I currently have the multimeter here just hooked up to two very thin wires that are coming out of that power supply. And if we turn this on, we're getting nothing. Oh, I think I hooked the ground lead up to the wrong pin on there. Let me fix that. Okay, I've moved the ground lead over. Let's turn this on. There we go, 24 volts. So what we can do is we can set this to something much more reasonable, like 5 volts. There we are, 5 volts. I'm going to change the current to, say, 10 milliamps. So on this little capacitor here, I'm going to clip this lead here onto the positive lead. I know, sorry, it's gray. And I'm going to clip the black lead onto the negative. And now when I connect this positive lead to the cap up, it should drop down because the power supply will go to constant current mode, and then it will slowly go up. Here we go. All right, so remember 5 volts is what this cap can actually charge up to. And what should happen is to hit 5 volts, and then the current draw should disappear. What I can do is unplug the power supply here, and now we're just looking at voltage coming from that cap itself, and it's slowly discharging. So that's good. Hook it back up. It jumped back up. So I'm going to raise the voltage up. Let's lower the current down. It's at 5 milliamps now. Let's raise this voltage up. It's creeping up slowly. And theoretically, to properly reform this is you really need to measure the current, which I'm not doing. And then we just need to let it sit here for a while. And basically, if it's drawing any kind of excess current, what you need to do is on a very, very low current, just let it kind of sit there and bake until it reaches the voltage and is no longer drawing any current. All right, EEVBlog multimeters here. It's showing some amount of current draw, even though the leads aren't connected right now. So we relative it out, I guess. Okay. So the positive lead that was going to the cap now goes into the negative lead on here, and I'm going to connect up the positive lead to hit the cap. And there we go, it's charging. Well, it was charging at like 4 point something milliamps, and now it's fading away to 0. And it should eventually reach a steady state. The cap is basically drawing 0.12 milliamps. And that might be actually kind of normal. The cap obviously needs to take a little bit of current at all times to charge. So let's raise the voltage up. So we're at 6 volts now. Let's go to 7. And our current limit on the power supply is set to constant current right now was 5. Yep. And then as soon as it goes below 5, then it starts to drop down here. Yeah, this cap seems to be working pretty well. Now, I think I did reform it not that long ago. So I'm just going to raise the voltage up here to, say, 13 volts. Let's let this go. So there it is. It's drawing 4.4 milliamps. All right, it's in constant voltage mode, which means it's reached the target voltage. And then we should see this drop down to 0.000. And it's currently showing 2 on here and 2 on there. Now, if this cap were unhappy and you're trying to reform it, what I think would happen is it would never reach the target voltage when you have it set to this really low current limit at 5 milliamps. It would just sit there kind of continually drawing 5 milliamps, trying to raise up to the target voltage you've set. And you just let it sit there and bake. And hopefully, if it's happy, it'll suddenly be able to reach that target voltage and the current draw will go down, and then you raise it up another volt, and then you let that process repeat. And you keep doing that. Now, one thing about this virtual bench is it's all scriptable, I think with MATLAB or something like that. So you could actually automate this stuff and you could read these values here coming back from the power supply, and you could use this to automatically do some scripted reformings, and you could charge batteries with it and stuff like that. There's all sorts of cool stuff you could do with this thing. So we were at 13 volts, but we're still at 0.8 milliamps. So it's not as low as I would have expected. I would have thought this would have dropped down to 0 by now. And that's not happening. So maybe I just do need to leave this thing and sort of let it do its thing. What is the voltage rating on this cap? It's 30 volts, 18,000 microfarads. So there's plenty of headroom there still at 13 volts. But I would really want this to drop down and be lower. So I think it is reforming right now. And best thing to do is just let this sit here until this drops to like 0.1 or less. And then I'll keep raising the voltage. Okay, it's been a bit of time, and I had it at 19 volts. It was down to 0.1 milliamps. I think that is good enough for the reforming process. I have it disconnected from the bench power supply, and it's slowly dropping. It was at like 19.0, and it's been a while now, and you can see how quickly it's dropping from 19 volts. So this cap seems to be holding a charge pretty well. The lead just fell off. So what I want to do next is hook this up to the power supply I've repaired and feed voltage directly into this from the bench power supply. And I want to see a nice solid 5 volts coming out of the regulator. That's a good way to test it. We don't even need the motherboard. We don't need that transformer, which I hope is still good because I'm doing all this work here without actually testing it. So let me get that all set up. Okay, we're all set up. The cap is hooked up. Bench power supply is connected. It's not powered up right now. And on this connector where I have the red mark, that's positive. This should be the 5 volt output. And that one right there, the middle pin, is the ground. That pin there is not connected. Now this is totally safe to do because nothing else on this board is currently connected to this 5 volt rail. This thing is completely isolated. It normally feeds the AC voltage in here, goes through these diodes to the capacitor, through the regulator, and then there's the adjustment right here, and then it comes out there. So when I power this thing up, and we'll just poke these leads into here, and I'll hold that in place. When I power this up and I have 9.5 volts currently set to go into the cap here, we should see 5 volts regulating on there. Here we go. There we go. 5.2 volts. Currently the bench supply is sending 9.5 volts, and it's, well, this whole thing is drawing 3 milliamps right now. So basically nothing. What I'm going to do is I'm going to lower the voltage. So now we are at 8.5 volts, 7.5 volts. If I get to 6 volts, which probably should start to see a drop on this. Let's go 6.5 volts. And no, it's, wow, it's still regulating. This thing is working quite well. I'm going to go up though. So we're at 7.5, 8.5, 9.5, 10.5, 11.5. Yeah, I mean, this is obviously regulating 13.5 volts, and we're still at 5.2. Maybe this is a little bit high, so I could try to lower this down, although I just noticed the voltage regulator here actually has a bit of like glue on it, the same stuff that was holding the cap down. So they must have done that, so they don't want this to be messed with. Poking at it, it's pretty stable. There's going to be some voltage drop over those thin wires that go from this connector down to the motherboard, so I'm betting it's going to run more around 5.1 volts under load on the motherboard, that is. Now, of course, what I haven't tested here, and I'm just going to shut off the bench power supply. Wow, the power supply is off. Like I can unplug that lead there. And we're still getting 5 volts. And that's because, of course, this cap here is working after doing that reforming or whatever. Ah, there we go, it's finally dropping. It will drop quicker, obviously, when there's a load of the motherboard. Nice, okay, this is what we expect to see. That means nothing was really damaged when this cap, well, went short and caused all that blast damage. So now the question is, should I clip onto the underside of this and try to power up the CRT? I'm presuming it's probably okay to do. Obviously the deflection yoke's not connected, nor is the flyback transformer, which connects right here. So this circuit just should sort of power up and we should end up with 15 volts. I think it's worth doing. For the CRT board, That's the bridge rectifier. We're looking at the back side of it. So the AC comes into that, and then it comes out, and there is one of the large blue capacitors. It's right here. And I can see that that pin right there, that is the negative rail. And this pin right here, that is the positive. And I'm just looking at the capacitor itself, and you can look and see which side has the negative stuff on it. And if we go from this cap here, from the minus rail or the ground rail, to the capacitor that's over here, which feeds this voltage regulator, the minus is right there, and that is correct, that matches. And the positive, I'm assuming, is going to be right there, and it is. Yes, okay, cool. So I'll just connect up the ground lead there. For the positive lead, I have just soldered a little resistor on there. There's a jumper link that goes from here to here that connects the bridge rectifier to this side of the board. Now I will add, by the way, that this only works because we're using linear regulators and not switch mode power supplies. Old switch mode power supplies don't always appreciate not having a load on them, but with linear regulators like this, there's absolutely no problem at all. So for this regulator over here, from an output standpoint, we're going to be picking up the voltage right here. We should be seeing 15 volts once the system is powered on. I'm just going to draw on here where we need to measure. So there's a green mark right there and right here. So these are two separate 15-volt circuits, and one of them handles horizontal deflection and one handles vertical deflection. For whatever reason, they decided to do two separate circuits. So when we go to ground here and they turn on the power supply, I should be seeing 15 volts here, and we should be seeing 15 volts there. And that's if nothing is shorted on this board. So I have the bench power supply now at 17.5 volts, 500 milliamps. And here we go, I'm gonna turn it on. Okay, so what it did is it current limited for a second, but now it's at about 100 milliamps or so. So let's see what we have here. 15.3 volts, looks good. We're still at 160 millivolts or so. And over here, where is it? This one? Yep, looks good. And the input side, 17.4, that's what's coming from the bench power supply. And of course this side, same thing, 17.4. And I'm going to try to hold these probes in place so you can see that, 15.3 volts. I'm going to turn it up the voltage. So 18, 19, 20, 21 volts, 22 volts. Yeah, it's looking good. It's nice and stable. And I'm going to turn it back down, 17.5, 16.5. Okay, so that's normal. Normally you need about 2 volts above the regulated voltage. This 5 volts seemed to handle that without a problem with just 1 volt. But these are just normal 78 15s, and you need about 2 volts. So that looks good, and down to 15.5 volts, and yeah, it's dropped down to 13.9, but that is no problem. So there we are, back at 17.5 volts, and things are looking good. Now let's unplug the power supply here, see how quick it drops. Drops pretty quick, but that's because there's obviously circuitry running on this thing. Don't worry, without the flyback and without the deflection yoke, there's no high voltage on this board. There would potentially be boost voltages and stuff like that once those things are connected. Right, so there we have it. This power supply board, as far as I'm aware, should work now. So all that's left to do is to bring the chassis over here and plug that thing into the wall. I'm not gonna plug this power supply into that. It's just gonna be the transformer on its own. And we'll measure the AC volts that are coming out of it, see what we're getting. Okay, so I don't have a wide angle lens for this Panasonic Lumix camera. I started looking that up actually, and well, they're kind of expensive, and I don't know, I should probably order one, maybe try to find a used one. It's a G Vario Micro Four Thirds type lens. And the lens I was looking at was from 7, oh, this is kind of bent up here. It was from 7 to 14 millimeters. That was the range of zoom. So that would make it a lot wider than this. I'd just have to switch the lens if I needed the wider lens. I'm gonna plug this into the wall. It's currently set to off on the power switch on the back here. And when I hit the power switch, the fan should start spinning, and that's a finger chopper because these things have a lot of inertia and they're AC powered. And then we should be able to measure the AC voltage coming out of these various windings. We have 2 blue wires, 2 green wires, and then we have 2 purple wires. The purple winding is the one that goes down to the motherboard, so that's for the minus 12 volt rail and the positive 12 volt rail. So I'm assuming we should see something like 18 volts or so on there under no load. And I'm not sure which is which on the blue and the green. One is for powering the 5-volt rail, which I'm assuming we might see 12, 13 volts or so under no load. And the other one is for powering the 15-volt rail. So we're going to see more like 18, 19, 20, 21, 22 volts. It really all depends on the transformer and like the design of it as far as how much voltage comes out of it under no load like this. The main thing we're looking for is a reasonable voltage out of all of these. We don't want to see something like 80 volts, 100 volts, anything like that. That's not right. All right, this is set to AC. Are we ready? Here we go. I'm going to turn this on. Oh, there we go. I thought the switch was bad there. That fan's a lot quieter than I thought. I'm actually shocked. All right, so we are on the blue wires here, and we're getting 25 volts. I'm just going to write that down. Next up, green wires, 11.4. So this has got to be the 5-volt rail. That's completely, absolutely acceptable and fine. Lastly, we have the purple ones. 40 volts, huh? That seems pretty high, pretty high. Now there was actually purple with a stripe on it as well. Let's check to see that going to these other purple wires here. 20 volts. Ah, okay. It's center tapped. Got it. So I'm going to try to draw a crude drawing of a transformer here, okay? So this is the primary side, so we're talking 120 volts coming in on this side, okay? And then we have the various windings over here that are the things we've been measuring basically. But what you have over here is one that's like that. So the purple wire, this is the purple, and then this was probably like green and blue. So on the purple winding, the purple wire with the stripe, it's got to be the center tap. And from that to any of the other two solid purple wires, you're going to get 20 volts. So if I go to the other purple wire here, we should have the exact same 20 volts. And we do, see? But from purple to purple, solid purple to solid purple, you're going to get double the voltage, 40 volts. As far as I'm aware, this center tapped arrangement is used anytime you're generating positive rails and negative rails off this. And remember, the purple wire goes to the motherboard, and that's for the minus 12 volts and the positive 12 volt rails. Right, so what's really great news here is the transformer appears to be totally working, and I'm going to say that these measurements I just took are completely within spec. Nothing here looks alarming in any way. That's a great sign. Secondly, the power supply, I think, is going to be working now. We haven't tested it under any kind of load, but usually with linear power supplies like this, if they work at no load, they're generally going to work fine under load, unless you have issues with the capacitors where there's a loss of value. You might get excessive ripple and stuff like that. But I know for the 5-volt rail, that cap is in good shape. I already did the reforming on it. Those other caps that are used for the CRT, I'm not so sure about those. But I think where this leaves us now is it's probably time to attempt to power this thing up. I think that's the next step here. And thinking about this, I think the right way to do it will be to just power up the PCB, the main motherboard, without the CRT stuff, and see if we get any kind of life out of the motherboard. We get any kind of like video signal. We should be able to see that on the oscilloscope here, coming through the sync signals and then the video signal as well. By the way, switching back to the desktop view here, this is the schematic for the power supply on the motherboard. And this is what I was talking about here. I should have looked here. Purple with white is the center tap on that winding. And that is used as, say, the ground reference for this entire circuit here, with the two purple wires going into the bridge rectifier, and that generates the plus 12 volts here, which is handled with a zener here, a 1N4742. And then the minus 12 volt rail is generated by the 7912, that voltage regulator that's on the motherboard. Meanwhile, the minus 5 volts actually is just generated by also a zener diode. Interesting, yeah, 1N4733. I'm not 100% sure why they didn't just use a 7812 and a 7905 for the minus rail, but that's how they chose to do it. And I guess maybe there's such low current draw on those two rails, 12 and the minus 5, that the zener is totally fine. The one thing about using a zener when you do these types of rails is the temperature coefficient changes the voltage and stuff like that. So I guess whatever's needing to use those, it just doesn't really matter that it can drift around and stuff like that. The reason why I was showing that schematic though is I wanted to show everyone that the 15 volts for the CRT does not go back to the motherboard. In fact, this is the connector on the monitor. This is the connector on the logic board. And notice that the connector on the monitor does have 15 volts on it, but it doesn't actually go to anything back on the motherboard. The only thing the motherboard is sending through to the monitor is vertical sync, horizontal sync, the video signal itself, and then the brightness and the contrast pots, or oh no, only the brightness pot is actually wired up here. The contrast pot is actually on the motherboard itself, and that controls the intensity of the video signal itself, the violet wire here. Meanwhile, I'm sure if we looked at the schematics, the brightness pot would go into one of the grid drives on the CRT to control the overall screen brightness. Very typical way that that works. And then the speaker is connected to the logic board connector, but it doesn't even go to the monitor connector as well. But anyhow, point being is that plugging in the power supply and not driving the CRT is not going to be dangerous. And as I mentioned, without the flyback and the deflection yoke connected, there's not going to be any high voltages generated on there anyways, even if those sync signals are making its way to the monitor. But I think what I'm going to do is I'm going to power up the motherboard without the connection to the monitor chassis at all. So obviously we need the power cables connected, but we don't need that video cable connected to the monitor. That way it's not even going to try to drive those circuits. The circuits will just be idle with that 15 volts available to them. All right, so let me get all set up. Okay, I think I'm ready. Keyboard's not connected. Obviously the motherboard's way over here. I got ground leads clipped together. Everything is good. The connectors are on the motherboard correctly. I am connected here, DC volts, into the 5-volt output so we can see what it looks like under load. Because there could be a short on here for all we know, drawing excessive current, and I don't know. Well, maybe we'll see it. These voltage regulators, though, are very powerful. This thing can pump a lot of current. Obviously, we don't have the load of the monitor powered up. The 15 volts is there, but there's no load on it. But honestly, CRT, like a monochrome CRT, doesn't use up a whole ton. This is the big current draw on a system like this. The connector for the monitor is right here. So if, there's that goop on it. Gross. Oh, it's even on that. I don't know. Okay, anyway, sorry, distracted. If the voltage rails look good when I power this up, the 5 volts is working well, then we'll hook up the scope probe here and I'll start probing around on there. We'll start looking for the video signals. I don't know if we're gonna actually see a video signal without the keyboard connected, for instance, or maybe there's a fault, but hopefully at the minimum, we should see the 2 sync signals. And plus I'll be able to tell if this is running at 15 kilohertz or whatever. Okay, are we all ready to go? 3, 2, 1. A beep. Sounded good. We're at 5.1 volts here, and that's before the voltage drop, so that's freaking good. Okay, this thing might actually be working. Okay, I think you can see the oscilloscope. See what we see here. Got a signal, that is clearly a sync signal. Yep, 15.6 kilohertz. So that's the horizontal sync. We're running at NTSC rates. The other one I'm assuming is 60 hertz, this one right here. Oh no, that's the video signal. Wait, there's an actual video signal. Yeah, I'm shocked, but this is without a doubt, that's a video signal there. We have some kind of video on this thing. All right, let's find the horizontal sync. I have this up here, pin 6, horizontal drive, pin 8 is the video, and pin 9 is the vertical drive. There it is, I just didn't have the scope set up correctly. There's the 60 hertz sync. So we have, yeah. That's why you don't want to get your fingers in these damn fans. We'll turn that off. The connector for the monitor fell into the fan there. Luckily, it wasn't my finger. We'll stop this. The stickiness, gross. Anyhow, as I was excitedly saying, there is the vertical sync, horizontal sync, and a video signal, and we had a beep. So that implies that this thing is freaking working. There's no CPU on this board. This thing is entirely TTL based, plus these asynchronous logic chips and stuff. How freaking awesome is that? Okay, I think I'm gonna end part 2 now because there's clearly still a bunch of work to do. I'm so excited. The power supply does actually work. Didn't have to switch to that switch mode power supply. The motherboard seems to be showing signs of life with some video. It could be garbage we're looking at, but there's some kind of video, and there's horizontal and vertical sync. And then the monitor section of the power supply board, that appears to be generating at least 15 volts, and the current draw doesn't seem to be out of the ordinary. So I think in the next part, the thing to tackle next will be the CRT, and I'm pointing to it over there on the floor. I'm gonna have to take that gross, sticky CRT out of there, put that spare one I had into there, clean up the wires and all that because it's all covered in this horrible goo, which is kind of brown. It's probably toxic. I need to get this off my hands. It's very sticky. And then see, when we power this up, what we get on the screen. We may still have to do a repair on this motherboard, and well, it's pretty complicated. Although in that manual, there is a full theory of operation, which hopefully gives us the right ideas about how it operates so we can kind of narrow down on any potential issues and problems and stuff like that. If we do end up needing to troubleshoot this motherboard, getting the RGB to HDMI hooked up to it obviously will be the right thing to do just to be able to work on this thing without the high voltage monitor sitting there, shock hazard, all that kind of stuff. But hey, really good progress in this part. I am so stoked to know that that power supply board appears to be working perfectly, and it was really just this bad capacitor that caused that horrible flame out event on there, and this thing went short, which is pretty shocking. Electrolytic caps can go short. I've had this happen before, but it's certainly not a normal failure mode. But this thing is old, and I guess its time had expired. Anyhow, if you like this video, I'd appreciate a thumbs up. If you haven't already subscribed to the channel, I'd really appreciate it if you hit that subscribe button. It really helps creators out like me. And of course, a huge thanks to my supporters. Their names are scrolling beside the screen, and they make it possible I do this full time. YouTube memberships and Patreon are possible. There's links down below to both. And I guess that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.